Yeah? Okay, now it is. I can. Thank you very much for the introduction and for the invitation to speak here. So I'm speaking about this work of Ellenberg, Venkatesh, and Westerland on the analog of the Cohen-Lenstra heuristic for function fields. I am a topologist by training. I don't really know any number theory. I'm going to focus on the topological part of the argument. It may surprise you to know that there is a topological part of the argument. In fact, most of the argument is in an argument in algebraic topology, essentially. But I want to start by explaining to you what the statement of the function field analog of the Cohen-Lenstra heuristic is, and then I'll explain a little bit the translation between that statement and a statement about counting points on certain Hurwitz schemes, and then I'll explain the translation between that statement and a statement purely in algebraic topology about computing homology of some spaces, or at least estimating homology of some spaces. And ideally, I would like to spend most of the talk explaining the proof of that algebraic topological statement. I'm certain that I will not get very close to that, but the notes that I've written for this exposition have a more or less complete proof of the topological part. So let's start. So here's the situation. Let L be a prime number. And then there's a measure on the set of isomorphism classes of abelian L groups, or finite abelian L groups. So there is a probability measure mu, the Cohen-Lenstra measure, on the set of finite abelian L groups, or isomorphism classes of finite abelian L groups. And the most important aspect is that the measure of a group is inversely proportional to how many automorphisms it has. So groups are counted just like you count points in groupoids. You count them inversely proportional to how many automorphisms they have. And then if I want to make this a probability measure, I have to put something on top that makes it add up to 1. And the correct thing to put is the product from I is 1 to infinity. So it's not very obvious that that is a probability measure, but it's true. It's very important that we take L groups. If you try to play the same game with finite abelian groups, it no longer converges. And for an odd prime L, the Cohen-Lenstra heuristic is as follows. So there's the classical case is the function field, is the number field case. But the case I'll talk about is the function field case. And it says the following. So for extensions of Q, for finite extensions of Q, imaginary quadratic extensions, we can look at the class group of L, of the extension field L, and we can look at the little L adic part of it. And the conjecture is that this is distributed according to the distribution mu. So these are a load of finite abelian L groups. We get one for every field, or for every imaginary quadratic extension, and the conjecture is that these are distributed as mu. And the function field version is the sort of obvious guess. For extensions now of FQT, imaginary quadratic extensions, and I'll say a word about what this means. The exact same statement. The L part of the class group is distributed as mu. And imaginary quadratic in this setting means not ramified at infinity. And what it really means is the following. It means things of the following form. It means extensions like that, where f is what? Square free. And I think of odd degree. Yes. So I guess the conjecture of Cohen-Lenstra is in the number field case, but everything I'm talking about today is going to be the function field version. So let me try to state as quickly as possible what the theorem that Ellenberg, Venkatesh, and Westerland prove is. I guess I want to fix an abelian L group. And I want to define two densities. So I'm defining two things at once, one called delta plus and one called delta minus of Q. And they're the limits of the following densities. So on the one hand, I want to count imaginary quadratic extensions. L of FQT of degree n. And by degree, I don't mean the degree of the extension, I mean the degree of the polynomial f of t that I wrote up there. And then I want to count how many of those have class group, or the L-adic part of the class group, isomorphic to the fixed abelian group A that I fixed at the beginning. So it's imaginary quadratic extensions L with L-adic part of that class group isomorphic to the fixed abelian group A that I chose. Also, of course, of degree n. And I want to take the limit as n goes to infinity through odd numbers because the degree of my polynomial had to be odd for this to make sense. And delta plus and delta minus are whether I take lim sup or lim inf of these two things. So there's two densities I've defined. One more little bit of notation before I can state the theorem. So I want to say a prime power Q is good for L. Okay, so there was an L that's been fixed the whole time. It's the prime such that we're looking at abelian groups of that order. And there's a Q, which is the field that we're working over. And I say that a prime power Q is good for L if Q is odd and L doesn't divide Q or Q minus 1. Yes, doesn't divide. And then the theorem is as follows. So this is due to Jordan Ellenberg, actually Venkatesh, and Craig Westerland. And I'll emphasize it again. Let L be odd. As Q tends to infinity, with Q good for L, delta plus of A and delta minus of A both converge to the Cohen-Lenstra measure. This is a sort of weak form of what's really been conjectured. If you interpret the conjecture a bit more literally, it would say that maybe for all big enough Q, delta plus equals delta minus equals mu of A. Okay? They prove the statement in the limit as Q goes to infinity along these good Qs, not for all big enough Q. But the conjecture is that it holds that they're equal and equal to mu A for all big enough Q. So as I mentioned in the preamble, the heart of the proof that they give is topological in nature. And let me spend the next few minutes explaining the connection between between this statement and the topological statement that one actually proves. So this will sound a little different to begin with. So for a finite group G and a conjugacy class C in G, we can consider G Galois covers of the affine line, which are branched, and whose monodromy at each branch point lies in the class C, and with a fixed number of branch points, say n. And there's a scheme that parameterizes those. So there is a scheme called HNG, G, N superscript C, parameterizing branched G Galois covers of A1 over whatever, with n branch points, each of which have monodromy in the conjugacy class C. Nope. What's down? Oh, I see. Down. And the first thing to do is to change the theorem as I stated it, and to I'll write it as a statement rather than a theorem, which is what's to be proved. So Ellenberg, Venkatesh, and Westerland show the theorem is equivalent, or follows, to follow from the following. So the setup's the same. L is odd, Q is good for L. A finite abelian L group. And then I want to put myself in the situation of these Hurwitz schemes. So I'm going to take G to be the following group. It's the semidirect product of plus or minus 1 acting on A by inversion. And C is the conjugacy class of involutions in that group. Sorry? Yes, or Z star, yes. Yeah. Acting by inversion. Questions like that I can handle. And the conjugacy class is the involutions. So I've now fixed the finite group in the conjugacy class, so I have these Hurwitz schemes available to me. And then the statement is as follows. There is a constant B that only depends on the abelian group, such that the number of points, the number of FQ points of this Hurwitz scheme divided by Q to the n minus 1 is bounded by B over square root Q for all big enough n and q. So I don't want to go into the details of this. Let me explain a little bit the connection between these two things. they first prove a measure theoretic result about the, I've erased it, about the Cohen-Lenstra measure, which is that here's an equivalent characterization. It's the unique measure so that the expected number of epimorphisms to a fixed abelian group X is 1. The Cohen-Lenstra measure has that property, and that property characterizes the Cohen-Lenstra measure. And then the missing step, which I won't say anything about because it's not the sort of thing I understand, is using some class field theory. They relate counting branch covers with respect to this sort of Galois data to epimorphisms from the class group to A. I think that's somehow more or less routine for people who understand it. But the question now becomes to prove this sort of inequality. And at this point, if I tell you that there's going to be some sort of connection to topology, it's sort of clear how that must arise. It must arise by trying to make this point count using the Grothendieck-Lefschetz trace formula. So what does that say? That says that we can make this point count the number of FQ points is given by the Lefschetz number of the Frobenius acting on the cohomology, on the entire cohomology of this scheme. So it's an alternating sum of the trace of the Q Frobenius acting on cohomology HNGNC Q bar with, I pick some other prime that's not Q or L, QR coefficients. So this gives us some sort of cohomological approach to this question, of course, but it involves knowing, firstly, what the entire cohomology is, and secondly, how Frobenius acts. And the second purely number theoretic input after the translation between these two statements is the following. I also won't say anything about this, but the trace of Frobenius acting on zeroth cohomology. What does that mean? So that is asking, I've got this scheme defined over FQ bar. How many irreducible components of it are FQ rational? And what they prove is that 1 is. And this is where being good for L shows up. In fact, being good for L shows up in two ways, L not dividing Q and L not dividing Q minus 1 separately. Here it's L not dividing Q minus 1. What they really prove is that all irreducible components apart from 1 have L fruits of unity in their field of definition. So if L doesn't divide Q minus 1, then it can't, and so you don't see those components. Also, incidentally, everything I'm going to say afterwards is not going to use this good for L in a very strong way. And you see, if L does divide Q minus 1, then you can still do this calculation and you get a different answer. And that different answer will tell you that the Cohen-Lenstra heuristic is not right if L divides Q minus 1, but it also tells you how to fix it. You correct it by whatever the other answer would be. So what does that say? Oh, I messed up here, of course. I should have written over Q to the end. So what does that say? That says if we're trying to prove this sort of inequality, the 1 is the 1. And what we have to prove is that all the other cohomology of this Hurwitz schemes don't ruin life for us. Right? Because if they have lots of cohomology, then the trace could overwhelm whatever we're doing here. Okay? I mean, one can use Deligne's estimate for what the eigenvalues of Frobenius are, but you then need to estimate, in order to, if you know what the eigenvalues are, if the group is still very large, the trace can still be very large. So you have to show that those other terms don't beat what you want to sort of first or zeroth order. So need to show this is not overwhelmed by contributions from higher cohomology. Here it's not compactly supported. I've used Poincaré duality several times, probably. So here I don't mean compactly supported cohomology.
This changes the topology.
Yes, it changes it like this. So how could we show that this overwhelming doesn't happen? It would follow if we could prove the following two things. It would be enough to know two things. I want to first say it this way. Firstly, that there's not more than x. So the variable now is going to be n. I'm going to talk about q is now more or less fixed, and I'm going to talk about varying n. Firstly, I want to say that there's not more than exponentially much cohomology in total as a function of n. Okay? That's actually not very difficult. We'll do that. I'll give you a complete proof of that. The second thing I want to say is that of that exponentially much cohomology, not too much of it is in low degrees. Okay? Low cohomological degree means relatively large eigenvalue for Frobenius. Okay? So these are the two things we want to show. I want to show that the dimension of each cohomology group is polynomial in n. And here it doesn't matter if I fix 1 degree or if I take them all together. It's the same question because there's only finitely many groups. And the second thing I want to show is, as I said, I want to say that not too much of it is in low degrees. I can say that in the following way. Let me write it and then I'll justify what I'm talking about. For n at least some linear function. Okay, and some capital N. So this is what we call in topology a homological stability theorem. What this is saying is if I fix some cohomological degree d and I let n increase, at some point it stops changing. Okay? And it turns out that for the statement that we're trying to prove, you need to know not just at some point that it stops changing, but you need to know that it's linear in d, the point where it stops changing. That's actually important when you come to do the estimates. But essentially that's what one needs. So that in each cohomological degree, the cohomology stops changing as a function of n once n gets past some threshold, and then there's some fine work about what exactly the threshold looks like, which I won't bother you with. Let me just write what the conclusion of this is. Together, just by putting these two ingredients together in the sort of naivest possible way, you get that the dimension of the deep cohomology is bounded by an exponential function. For what? As long as n is bigger than some constant time to dimension. Okay? This is completely elementary. Let me just briefly say what it is. I look at this cohomology group. I decrease little n in steps of capital N, as many times as this lets me do it, which is some linear function of d, and then I use the exponential estimate for the smaller thing. Okay, and that immediately gives that. But if you have an estimate of this form, you then are done, because Deline's estimate for the size of eigenvalues will beat this if you take q bigger than C1. And so in the limit as q goes to infinity, that won't contribute at all. So this is my sort of brief connection between the statement of the theorem and what I want to claim is a topological statement. Because here, these two statements, they're not about how Frobenius acts or anything. They're just about the dimensions, essentially, of the étale cohomology groups. And if you have a comparison theorem between étale and singular cohomology, which in this setting you do, is then a question about the singular cohomology groups of a space. And then people like me or Westerland can get to work. So let me just say, so with a comparison theorem, of the form étale cohomology is isomorphic to singular cohomology of the complex points in the analytic topology. A and B are topological questions. So the problem now becomes to understand the topology of the space of branch covers of the complex line with n branch points and with certain details about what the Galois group is and what the monodromy is. So let's start doing that. Let's start by thinking about how we can connect the topology of this space of branch covers of the complex line with maybe some more familiar spaces. Here's the first thing we can do. If I have such a... So let's just remember what this is. This is the set of branch covers, or G Galois branch covers of C with n branch points and monodromy in the conjugacy class C. So given such a thing, I can just remember where the branch points are. Forget everything else, just remember where the branch points are. That gives me a map to the space of configurations of n distinct points in the complex numbers. So this is just remember or record branch points. Yeah, just remember where they are. And suppose I have some configuration of n points. What's the fiber of this map over that given configuration? So I'm now looking at branch covers with fixed set of branch points and certain monodromy and certain Galois group and so on. Okay, but that's just covering space theory. Right? If I want to, so now when I remove the branch points, it's not branched. And so what data do I have to give such fixing the psi? What do I have to give this? I need to give you a representation of the punctured complex line to G. Okay? And I forgot to say some things here, for example, connected. If I forgot to say it, I meant to say it in the definition of HN as well. What does being connected, by which I mean the total space of the cover is connected, what does that mean here? It means it's a surjective homomorphism. Right? We get any Deck transformation we like. And what else? I've missed something. Oh yeah, there's a bit of yoga of base points to deal with because I haven't picked any base points, and so I ought to take this and I ought to divide out by the conjugation action of G, because I don't really have a preferred base point in C minus Xi. I can pick one. But that's what the fiber is, and that's just a set. Oh yes, and the monodromy condition is that rho sends, let me draw a picture. I can pick somehow a base point and a load of arcs going from little curves around each branch point, and I can ask that each of those is in the conjugacy class C. And that doesn't matter how I pick the tethers because it's up to conjugacy anyway. Question?
Yeah, what would happen if you replace your single conjugacy class by saying?
So you could, for many things I'm saying, you can fix the conjugacy class by any conjugacy invariant subset. But for the example that's relevant to their theorem, it's a single conjugacy class. It's the conjugacy class of involutions in this semidirect product. So if I just choose some of these, it sends each xn into C. But that doesn't change the point I tried to make a minute ago, which is that this is nothing but a discrete set. So this map pi is nothing itself but a covering space. And the base is very well known in topology. It's a classifying space for Artin's braid group. It's a k-pi1 for the braid group. So to give a covering space of that, I just have to describe to you an action of Artin's braid group on this set. And of course, it's the obvious one. It's obvious to topologists, right? The braid group is diffeomorphisms, basically, of the punctured copy of the complex numbers. And if I have a diffeomorphism, I just act on the homomorphism by precomposition. So this is, in fact, there's a more, so thus pi is given by an action of pi1 of this configuration space, which is beta n Artin's braid group on this set. For some, I have to pick some configuration to start with, but apart from that. And let me just say briefly how that action looks if you do what I said here and pick some xi's. Because when I remove the configuration xi from the complex line, what's left is just up to homotopy a wedge of circles. So its fundamental group is a free group on these xi's. So giving this homomorphism is the same as saying where each xi goes. And so really, this is the same as saying I have to give you a list of elements of G, n elements. They have to generate G. That's the surjectivity. And they're given modulo conjugation of the whole tuple. So another way of writing this is C to the n, such that they generate the whole group, and again up to the action of conjugation. And from that point of view, the braid group action is very easy. It's quite pretty, so let me tell you what it is. If I have this braid, I and I plus 1, up to n, and I want to act on such a tuple, it's given by conjugating the ith thing by the I plus first thing. Or vice versa. These things Okay, I can now prove A. or rather we can now appeal to Arnold to prove A, because Arnold has found a cell structure on the space of configurations that has 2 to the n cells. This is a cover whose fibers have size c to the n. So in total, this has a cell structure with 2c all to the power n cells. So the number of cells is a very coarse way to estimate how much homology something has, but of course it's a valid way. Conf nc has 2 to the n cells, and so we deduce that hng nc has 2 times the size of the conjugacy class to the n cells, which implies part A. Then the amount of homology is the most exponential. So that part is that wasn't very difficult. No. Yes. Actually, Arnold's cell structure is very pretty. Let me just draw one picture, and then you see the picture, and then you understand completely. Let me think of configurations in a square instead of in C, but it doesn't really matter. I can stratify by how many real values a configuration has. Each point has a real and an imaginary part. Just think about what the projection onto the real line is. And in general, what I find is that I have some vertical lines, and each one has some number, maybe different numbers, of points on them. That's the sort of a bit of combinatorial data I can get from any configuration. You know, generically, they'll all be different, fine, but sometimes they'll be the same. But if I think about configurations that give this kind of combinatorial data, that's a cell. These walls can move back and forth, and the points on each wall can move up and down. The whole space is just a big cube. And my configuration space is covered by these cubes, and that gives a cell structure, and then you do a little count of how many, given endpoints, how many combinatorial types are there? 2 to the n. In fact, 2 to the n minus 1. Okay, now let's get on to the, so this was somewhat topological, but the more serious algebro-topological input is yet to come. And I want to first make a topologist version of this Hurwitz space. Which I'm going to, it's going to give it a very similar name, but that's fine because it's a very similar thing. I'm going to call it HurGNC. And it's the following space. So is the set of tuples T, Xi, and F, where T is just a real number. Xi is a configuration in the cube, but which cube depends on T. Okay, so it's a configuration in a rectangular width T. So it's a finite configuration. And lastly, I want to give the data of a branch cover with Xi as the branch points, but we know how to do that. I just have to give a representation of the fundamental group of the complement. So the third bit of data is the topologist version of a representation of the fundamental group of the complement, namely it's a map from the complement to the classifying space for G bundles. So it's a map to the classifying space for principal G bundles from this cube minus Xi. And I now want to sort out as well my base point issues that I had before, such that I don't want to write out the formula, but 3 sides of this square go to the base point. Okay. In homotopy theory, anything contractible is the same as a point. So really all I'm saying is I've trivialized the G bundle over some point at infinity. But in topology, we can just trivialize it over 3 sides. It's a bit more convenient. And this has a topology that I'm sure you can all imagine, right? If I wiggle the points a bit, I know what to do on the complement. There's something to work out there, but there's a sort of obvious topology. T can stretch and shrink, the configurations can move around, and the map can change by a homotopy. And what is the connection between this and everything I said earlier? C as well, I should be part of 3. It's exactly the same statement. Each little loop around a missing point goes to a loop in BG that's, the fundamental group of BG is the group G, and so it goes to a loop that's in the conjugacy class C. So each loop around a point in Xi goes to C, which is a conjugacy class in G, which is the fundamental group of this space BG. Serious. It's the completely analogous condition. So I've done, I fixed 2 things that I consider to be a problem with that up there, or even better, this formula that I wrote here. One is that dividing out by this conjugation action is somewhat irritating, and I'd rather not do that. And I fixed that by fixing the bundle over this, essentially a point, or over 3 sides of the cube. That gets rid of this dividing out by G. The other thing I fixed is that I haven't said that this classifies a connected cover. I just take it, I'm allowed any map as long as it goes here. So I haven't, in my formula up there, I don't have to write the condition on the right that these elements generate the group. I'm allowed any sequence of elements. But those are the only differences. So let me just say, forgetting F gives a map to, ideally I'd like to say it's configuration, well, I can write it as configurations of C. I only happen to get configurations that lie in a rectangle, but whose fibers are a sort of fixed version of that. They're just G1 up to Gn in C to the n with no conditions. In other words, it's the set C to the n. So there's no dividing out by G, and there's no such that blah, blah, blah is connected. So I have a subobject, or subspace, C her. So this classifies connected covers. So such that the property is that this map is surjective on fundamental groups. And I also have an action of G, because G acts on BG by conjugation. G acts on itself by conjugation, of course, and B is a functor, so G acts on BG by conjugation. And that exactly corresponds to re-trivializing my bundle over the marked point. And if I take the quotient for that action, then I really have got if I take the quotient of the connected Hurwitz space, or the connected topologist Hurwitz space, that really is homotopy equivalent to the complex points of the algebrogeometric one. Basically because they both fiber over the configuration space, and the fibers are, I've arranged for the fibers to be the same. So we wanted to show this homological stability phenomenon for these spaces. That was the goal. It seems distant now, but that was the goal. That means I need to show homological stability for these spaces, with rational coefficients, essentially, or with characteristic 0 coefficients. Dividing out by a finite group action is a very safe thing to do if you're computing homology with rational coefficients. So really, it's enough to show that these connected Hurwitz spaces have homological stability with maps that are G equivariant. If they are, you can then just quotient out by G and you'll get it. So it's enough to show that C, her, G, N, C have homological stability with a G equivariant stabilizing map. Right? As long as the isomorphism that compares n points with n plus capital N points, as long as that's G equivariant, I can divide out by it and that will be safe. It turns out that it's easier to prove stability for the non-connected version and deduce it for the connected version by a sort of downwards induction. So I want to not do that and just talk about the version her with no decorations. Okay? So case of C, her, G, and C follows from her, G, and C by an easy argument. Okay, so the problem has now become translated to this topological setting. We can forget all the C and the G and everything. We can just work with these spaces. We need to show that these spaces, their homology is independent of little n in a range of degrees that grows with n. That's the problem. And I want to give you an idea for why I've put these sort of conditions on that space. It may seem that all these things are basically as complicated as each other, but the one I've arranged there has much better properties than all the other versions that have been on the board, because it has a multiplication. If I have two branch covers of a rectangle, sorry, if I have two branch covers of a rectangle, I can put the rectangles next to each other, and I get a branch cover of a bigger rectangle, as long as, where I try to do the gluing, I've trivialized both the bundles. But luckily I have, because I insisted that my vertical walls had trivialized bundles over them. So this space has a multiplication, which means that the homology of all of these spaces put together is a ring. So note, if I take the totality of all these spaces combined into one object, it has a multiplication. If I want to multiply, I sort of have to draw a slightly schematic picture for what the data is, but the data of a point up there is a t, a load of configuration points in the cube of width t and height 1, and something I can't really draw, which is a map f from the complement of psi to bg. But if I have two such pictures, oh, and with this condition that the map is constant to the base point along there. And if I have two such pictures, I just put them next to each other. I think of it, this one, instead of starting at 0 and going to t prime, I think of it as starting at t and going to t plus t prime. It has its own configuration, and it has its own map. But I've arranged that if I just put them next to each other, that's a valid point in my Hurwitz space. The number of branch points adds, the map's glue, and this is fine. So the homology, or the totality of these homology groups with some coefficients is a ring. And if we've got a ring, then there's many obvious candidates for ways to stabilize, namely just multiply by any element in the ring. I want to compare homology groups of the same degree, so I better multiply by classes in H0. I.e., I ought to fix one such picture and stabilize by gluing many copies of the same thing on. Right. Let me call the homology of the nth term Rn, and the whole thing R is a ring. And let's just calculate. It's very easy for us to calculate what the zeroth homology is. What is, no, sorry, that's not Rn. And that's not R. Sorry, I take it back. It's true what I said, that this is a ring. And I want to write R for its degree 0 part. So the zeroth homology. And I'll call that Rn. Okay? It's very easy to work out what these Rn's are. It's sort of in some sense. We can give names to all the elements. What is Rn? Rn is the K module spanned by tuples G1 up to Gn modulo the action of the braid group. And the action of the braid group said that G1 up to Gn is equivalent to G1 up to Gi minus 1, what is it? I had this formula somewhere. Gi. Okay, but we have names for every element of this abelian group, except that they're not very unique names, and so we have to, that's somehow the problem. And the first, and somehow the thing that gets their argument started, is that, so this is a very complicated non-commutative ring. The ring structure is just concatenation of such symbols. It's not commutative. And they prove that this very complicated and strange ring contains a polynomial ring in one variable that's central, and the whole ring is finite as a module over that. So it's actually not very far from just being a polynomial ring in one variable. Let me try to record that. So this is one of their propositions. If the pair GC has a property called the non-splitting property, which I'll define in a second. I'll define it there in a second. And the order of the group is invertible in the field, then there's an element, capital U, in one of these things for some big N, such that U is central, and multiplication by U, left multiplication by U, let's say, going up capital N many terms, is an isomorphism for all big enough N. Okay. If you think about what that means, it means precisely what I said, which is that it contains a polynomial ring in one central element, and the whole thing is finite as a modulo of that. It exactly means this, but this is somehow the way to prove it. And the non-splitting property is just the following. It says that the conjugacy class, when I intersect it with a subgroup, it's either empty or it remains a single conjugacy class. For all subgroups of G. And it's a little exercise for you that if I take the semidirect product of Z star acting on A by inversion and take the conjugacy class of involutions, that has the non-splitting property. Because there's not so many subgroups to check. So in other words, what they've shown is that the zeroth homology of these Hurwitz spaces stabilizes. These Rn's are just the zeroth homology of these Hurwitz spaces for different n. Okay, and the proof of this just uses this description and games in the braid group. Okay, this is not. I mean, it's sort of very elementary, but clever. In ordinary settings where we study homological stability in topology, you have a sequence of spaces, x1, x2, xn, and you want to prove that homology stabilizes. Usually, each xi is a connected space. And so the fact that there's zero homology stabilizes is not very impressive, normally, because all these spaces are connected. The point here is that these individual spaces for a fixed n have very many different components. And the stabilization maps mix them up in some somewhat complicated way. And the remarkable thing, I mean, it's sort of remarkable that it's true. The second remarkable thing is what this element u is. It's very much not what every topologist would guess it should be. Every topologist would say, here's what you do. You pick one very complicated branch cover, and you glue on that many times, and you should have stability with respect to that. Like take one where every possible monodromy shows up, or take one connected cover where every possible monodromy shows up. There u, firstly, it's not a point in a space. It's a linear combination of points. Their map u is only defined on homology. It's not defined as a map between the spaces. That's why no topologist would think of doing this. And what it is not so difficult to say what it is. It's I take the branch cover with monodromy G. I do this for all possible Gs. And each one I do its order many times, so that the global monodromy is trivial. And then I do that some very large number of times. That's a little bit out of control, but it's some fixed number. That's what u is. Okay, but it's a sum of geometrically defined maps. It's not a composition of geometrically defined maps, so it's not defined at the level of spaces. So it's already very interesting that the zeroth homology of these spaces stabilizes, and the problem now is to decide how you're going to upgrade this to prove that all the higher homology groups also stabilize. And the key point, of course, is because all of the homology groups together formed a ring, all the d homologies of all the Hurwitz spaces are a module over this ring R. And we know R is, roughly speaking, a polynomial ring up to this finite amount of noise. And the problem is now to somehow work out how to leverage that. And Ellenberg, Venkatesh, and Westerland leverage that in one way, which sounds quite geometric, but that's a little misleading. In my notes, I've explained a different way to do it, which is somehow a little more homotopical algebra in flavor. I just want to give you some idea of the inputs there. So the strategy, so use that the sum over all n of the dth homology groups for some fixed d is a natural numbers graded R module. And now there's different ways you can start trying to use this, but this is somehow the insight. That R has this good, it's roughly speaking a polynomial ring in one variable, and all of these are modules over that. And so we have a candidate stabilization map, namely multiplication by the same element u, and we want to show that that's an isomorphism in some range. So this will be a little bit impressionistic now. If I have some endomorphism of a thing, maybe a graded thing, like these are, so it goes between different components, saying it's isomorphism in big enough degrees, so all these are graded, maybe it's meant to go that much. Saying it's an isomorphism in big enough degrees means that the kernel vanishes in big enough degrees and the co-kernel vanishes in big enough degrees. But the kernel and co-kernel of these two things can be fit together into one homological algebraic object, namely a module with an endomorphism is just a module over the polynomial ring in one variable. And I can take Tor of M over the polynomial ring in one variable, so the derived tensor product. And Tor 0 is the co-kernel of this map, and Tor 1 is the kernel of this map. So saying both vanish in a range is exactly saying that this derived tensor product vanishes. So this has an extra grading, and it's saying it vanishes when the homological degree is large compared with the grading. So stability, this is just a reinterpretation, but stability is exactly a vanishing line for homology of this. So it's Tor 0 and Tor 1 vanishing. Tor 0 vanish. What does Tor 0 calculate? Tor 0 calculates module indecomposables of M as a KU module. That's what Tor 0 is. I mean, Tor 0 is derived functors of what I would like to think of as indecomposables. Tensoring with K over KU is taking indecomposables. And Tor 1 calculates syzygies, or it calculates relations as a module. Okay? So a vanishing line for the homology of this is precisely saying that it's finitely presented. It's saying all the generators arrive before now, and all the relations arrive before now, but it's a quantitative now. Okay? Of course, KU is no theorem, so if you know it's finally generated, it is finally presented, but you want to know when it's finally presented. So this is quantitative finite presentation of M as a KU module. So that's what stability is about. But once you start phrasing it this way, you see you can play other sorts of games. Like the KU module structure on M comes from an R module structure. So I'm allowed to compute things like M tensored over R with K. And by the same general principle, what does that measure? That measures presentation for M as an R module. Okay, except that R, this crazy ring here, R, is now no longer Noetherian. So we don't just have Tor 0 and Tor 1, we have all sorts of other things, and so it's keeping track of all the syzygies of some presentation of the module. And you might think, because R, and this is true, that because KU is central in R and R is finite over KU, being finally presented as a KU module and as an R module are not really such different things. And that's true. You can go back and forth with vanishing lines for presentation as a KU module and as an R module, using their theorem, that it's finite as a module over it. So you can rethink of this stability as asking, are these, this is what M's meant to be, incidentally, are these modules finally presented as R modules in a quantitative sense, and with higher, not just generators and relations, but relations between relations and all the rest of it. So that's another way of saying it. Of course, it doesn't really suggest how you might answer that question. And another observation is that R is the zeroth homology of these spaces put all together into one object. And maybe it's a better idea not to take homology. This is a good principle in topology in general. It's a good idea to take homology as late as possible in the game, because then you could do more functorial things along the way. And so rather than just take the zeroth homology, I want to make a differential graded algebra which is just all the chains of all the Hurwitz spaces. This is a differential graded algebra, and R is just the zeroth homology of A. Right? I mean, this is just chains, and in particular, there's a map from A to its zeroth homology. So any R module is also, in a very degenerate way, an A module. And you can play the same game. Maybe a presentation as an R module is not so different from a presentation as an A module. Now, of course, you might think that's a lot worse. A question, right? This looks very complicated. But there's a sort of miracle, and I'll say this and then I'll stop, which is that in some sense the algebra A is a lot simpler than the algebra R. And it's the following sense. The causal dual of A is very simple. That's the statement I want to make. The causal dual means how do I build K as an A module? Right. To build K as an A module, that's a very complicated thing to do because K is very far from being A. And this derived tensor product computes how to build K as an A module. And it turns out, here's the answer. So the homology is bigraded by n, which is this number of branch points, and d, which is homological degree. And it's incredibly simple. If n is not d, then it's 0. And if n equals d, it's the vector space with basis c to the n. And not only that, what I've made here is the bar construction of A with k over k, so it's naturally a coalgebra. And this is a well-known coalgebra. This is the so-called quantum shuffle coalgebra. On Kc. So Kc is a vector space, but it has an interesting braiding because C acts on C by conjugation. So you can make a deformation of the tensor coalgebra where you use that non-trivial action every time you swap something past each other, and that's the so-called quantum shuffle coalgebra. But somehow this causal duality is a duality. You can go back and forth. So somehow this algebra A has no more information than this thing. It somehow can't do because you can go back. And when you've got an algebra whose causal dual is very simple, that tells you it's very easy to compute homology over A, i.e. tensoring over A. There's a small complex that does it called the causal complex. And using this, you can show that sort of finite presentability over R is roughly comparable to finite presentability over A. But because of this business, there's a very good way to get at finite presentability over A. It sounds incredibly stupid. Here's a very stupid thing to do. K is what I get if I tensor A over A with K. But I can, when I write it this way, I can filter this A away. And I get a spectral sequence that goes to the homology of that from Tor over A, whatever, of homology of A, comma K. But it's converging essentially to 0. Because I know what the answer is. And this is telling me that these Tor over A's, this is just this derived tensor product, it's working out how to build the homology of A as a module over A. That's exactly finite presentability over A of A itself. And you have a spectral sequence going to 0. If this were 0, we'd be done. That would be saying, not being 0 in a range. We would be done, that would be saying that the homology of A is very finitely presented over A, so it's very finitely presented over R, so it's very finitely presented over Ku, and so it has stability. But one doesn't know that this that this collapses. Something could happen along the way, right? And so there's an important step in the argument, which is where you prove that A, the DGA A, has something like finite Castelnova-Mumford regularity. Meaning that if I know some module has a vanishing line for Tor 0 and Tor 1, then I have an explicit estimate for all the higher Tors vanishing. And you're then in a situation which I can, this is a sort of caricature of the situation. I have a spectral sequence. This is the Tor direction, and this is the internal homology of A direction. I want to prove that everything is, roughly speaking, 0. I do that by induction on homological degree. So down here, by induction, I've supposed that nothing happens. And I know the spectral sequence converges basically to 0. Now these two groups, oh, I've also drawn the wrong page. The first differential goes like that. These two groups have no way to die in the spectral sequence because they could only have died from lines below, and by induction, there's nothing on lines below. So Tor 0 and Tor 1 of the Deith homology, one has a vanishing estimate for them. But then by Castelnova-Mumford regularity, if you know generators and relations, you have an explicit vanishing line for all the higher syzygies. So once you know those vanish in a range, you actually get that a lot of this row vanishes in a range. And then you can move up to the next row. That's basically how it goes. Sorry for going over time. Thank you a lot for your patience.
Maybe I'll ask one. So in the Cohen-Lenstra heuristics, there are also independency properties with respect to L's, and saying that if I mean, the expectation that a class group has a 2 and 3 factors.
Oh, I see.
This is the product of, it should be for 2 and 3, and do this kind of ideas shed light on that question as well?
I think that's too far on the number theory side for me to have an opinion about. I don't really know. I don't know.
So in this construction of the of k times k over a, you explain the shuffle term, but what's quantum here?
Oh, it's the fact that so if let's see, this looks like. It looks like it more if I rewrite it like that. That looks like the tensor coalgebra on Casey. And my claim is that it sort of is that, except it has a deformed coproduct. In the tensor coproduct, I just use a braiding on this vector space, which is the usual braiding. AB goes to BA.
Sure. That's shuffle.
And here, that's just shuffle exactly. Here, I'm using the quantum braiding, which is that AB goes when I try to cross an A and a B over each other, they're both elements in the conjugacy class, so I can act on A with B. So I get something like that. So it's, yeah, if this had a trivial braiding, then it would just be the usual coalgebra, but it's a sort of deformed one. Thank you.